All right, this is kind of section 2.3. It's has to do with our project. This is iterated function systems. And I'll do it with just a size 2 here to begin with, a 2 by 2 and size 2. And so an iterated function system is just a collection of well, for us, just a collection of affine transformations. So we have a collection of affine transformations. Okay, affine transformations. Let's see, in recurrence relations. Okay, so an example. Now, they do have to be contraction mappings, and so we'll look at that in a minute. But here's just an example of something. So I'm going to use, say, something like 0.4, 0.2, 0.3, and 0.4. Something like that. So there's a matrix times, some xy, and then maybe I'll add to it, I don't know, how about 1, 0. So there's one function of x and y, or okay. So I have a 2 by 2 matrix times my two-dimensional vector xy there, and then plus a constant, and that's an affine transformation. It's also a contraction mapping, but we won't worry about that for the moment. And then I'll do another one here where maybe this is a 0.8, a 0, a 0, and a 0.5 times x, y, and then plus, how about 0, 1, like that. Okay, so here, I'll say is F1, here is F2. They are both affine transformations, and if I start with some point, so suppose I take my first point, my first vector x0, and that's the vector 1, 1. Then what I can do is look at F1 of x0, and that will give me 0.4, 0.2, 0.3, 0.4 times 1, 1 plus 1, 0. And so that is equal to, it looks like 0.6, 0.7, like that, and then plus 1, 0. And so that is 1.6 and 0.7. Okay, so that gives me that new point. But notice I started with 1 point, but now I'm going to do F2 of x0. And so that was 0.8, 0, 0, and 0.6 times my 1, 1 plus 0, 1. Like that. So look back. Oh, I was wrong. 0.5. Sorry. Okay. 0.5. And so that's equal to, we'll get a 0.8 and a 0.5 from our multiplication plus 0, 1. And so that's equal to 0.8 and 1.5. Okay, so notice what happened in this recurrence relation. We started with x0, and now we kind of have these two x's, and so I might go back here and call this one x1, 1, and this one x1, 2. Maybe call it equals. So there are my vectors, x0. I didn't put my line over my vectors there. And so this set, it was only a single vector, but this set became a set of two. You know, my set x1, if I think of that as a set, it's a set that contains x11 and x12, and so I have 2 points. Now, if I operate on that with my iterated function system, I will now have 4 points, because I will end up with an x21. I'll have an x22. I'll have an x23 and an x24. And I'll define each of those as this will be f1 of x11. This will be f1 of x12. This will be f2 of x11. And this will be f2 of x22. And so, you know, I have my matrix, I think it was 0.4, 0.2, let's go back and find it here, yeah, 0.3 and 0.4. Okay, so then that will be times my x11, which was 1.6 and 0.7. And then plus my 10. And I don't know what the heck that is. I get a 0.64 plus 0.14. So I get 0.64 and 0.14. That's 0.78. So I think I get 1.78 for that term. And then I'll get 0.48 and 0.28. So that's 0.73. So I think I get that vector. And similarly here, I would take the 0.4, 0.3, 0.2, 0.4, and multiply by the 0.8 and 1.5 plus the 1 and the 0. And let's see, so that's 0.32, and 0.2 times that is 0.3, so 0.32 and 0.3 is 0.62, and add 1, so I think I get 1.62. And 0.24 and 0.6, I think, so I think I get 0.84 for that one. Okay, and I keep going. All right, you don't want to see me keep going with that, but so I'll get 4 points. Okay, so my sets, the size of my sets were, you know, I started with 1 vector, and then I had 2, and then I'll have 4, and then I'll put each of those 4 into another one. That'll be 8, and then 16, and then 32 vectors or points in that set. And so what happens is these sets just keep getting bigger and bigger and bigger. And in this case, I'm multiplying by 2 each time. Okay, there were 2 iterated functions and in the system. And so however many points or vectors I started with, I then multiplied by 2 each time. So had I started with, say, 5 vectors or points, then my next one would have had 10, and my next one would have had 20, and then 40, and so on. Okay, because each time I took all of the set and evaluated it with 2 different functions, 2 different affine transformations. So these sets quickly get pretty darn big, and so what's the deal with all this? Well, the reason these are sort of nice is that actually, look at what it takes to define an iterated function system like this. Okay, for each function, I need 4 numbers here, plus those 2 numbers there. So for each function, I need 6 numbers. So, for instance, if I had 4 functions in my iterated function system, then I would need the 6 numbers for each function. So then I guess that would be, I would need 24 numbers total. Okay, however, if I do it just right, what happens is you can get these iterated function systems such that their sets make images. So these points or vectors that I have here, but if I plot them as points, they begin to look like an image. And that's cool, and that's what our project is doing. And so, for instance, our project uses an IFS with 4 functions. And if I start with a single point or a single vector, it will make a bunch of points. We're going to actually use something called the collage theorem, and I'll talk about that in another video. But this IFS with the 4 functions, you see that's 6, that's 24 numbers I need to know to transfer. But the image we're going to make ends up being a really cool looking fern, just like this. I know you're saying that's not a cool looking fern, but it could be. And so, I've just made that picture of a fern, but that picture requires a whole lot more than 24 points or vectors. And so what have I gained with an iterated function system? Well, I've gained the ability to store it. I can store this picture, okay? Storage and then transmission. I can make those if I can describe the images with an iterated function system of just 4 functions. You see, all of a sudden, my storage, I only need to store 24 numbers, and if I need to transmit them, I only need to transmit 24 numbers. And then it can get to its destination, and the person at the destination can run the function system, the iterated function system, to create the set of points recursively. So how many is enough? Well, that would depend on the image and what you're doing with it and that sort of thing. Okay? So in our project, we start with showing how we can take just 24 numbers and generate a picture that looks much like a fern. And in our case, instead of starting with a single vector, we're actually going to start with a polygon. And so it would be more like this case where we start with, say, 5 vectors or something like that, and generate our image from that. And that's just to kind of help us see how these images are generated. But I think these are really neat. They're very intriguing to me, and hopefully you'll find them at least somewhat interesting. Okay, so that's what an iterated function system is, and all it is. It's just these affine transformations that I define and then use recursively on a set of points. But because there's there's multiple functions, the set of points, every time I do a recurrence relation, it gets bigger by however many multiple of however many functions I have in the function system. So in our case, it just got bigger by 2, but it can get even bigger if it's 4 or something like that. And just to finish off here, I guess I should mention this. It needs to be a contraction. Okay, so for a contraction, geometrically, what we're looking at is that if I, say, start with, a figure like that after I put it through one of those affine transformations, it has to be smaller. Now, it can be morphed in some way, it can be skewed and all that, but it has to be smaller. That's a contraction mapping. Well, notice, that the translation part, the constant, adding the constant, that doesn't do anything. I mean, it just moves it either up or sideways or, down or, sideways, or both. And, so that keeps it the same size, but it doesn't make it any bigger either. So the constant doesn't really matter. It's the matrix A that we're multiplying by, the linear transformation part of the affine transformation that matters. And as a practical sort of thing, what we see, and this is part of your project to show this based on some definitions, is that if I have, A, B, C, D here for the linear transformation part of my function system, that particular matrix, what I need is that the maximum of the absolute value of A plus the absolute value of B. Okay, so think of these as absolute values because they could be negative, but if you look at their absolute values, the maximum of that with the other row, so C plus D, so the maximum row sum under absolute value, or column sum, A plus C in either column, B plus D, there we go. If that maximum is less than 1, then we definitely have a contraction mapping in the way we look at it, our geometry of the Euclidean geometry. Okay, so it's not an exact thing, but it's a nice rule of thumb that's very, very easy to check. I can very quickly just look at these, and if we look back at the matrices I used, well, actually, where did I define them? Back here. See, I've got, if I go, the first row, I get 0.6, the second row, I get 0.7, first column, I get 0.7, second column, I get 0.6. Those are all less than 1, so, yep, that's a contraction mapping. Here, definitely rows and columns, the maximum is 0.8. Here it was 0.7. Definitely less than 1, so that is a contraction mapping. So there we go. That's how I knew they would be contractions. And what they make, I have no idea. It may not be anything recognizable. It may not be anything interesting. But they are contraction mappings, and therefore we call them, under that context, an iterated function system, with, in their case, with two functions. Okay, so that's iterated function systems.